For section 11.11, we go over applications of Taylor polynomials, which is, well, it's kind of weird that we will really not going to cover the applications to physics, which is what the book covers. That is applications to optics, even though, well, there's a bunch more applications in chemistry as well when you work with ideal gases, and you can develop these temperature functions or pressure functions or volume functions in terms of Taylor polynomials and the like, well, those of you who are going to take physical chemistry or thermodynamics, depending on what your major is, well, you may get to see these Taylor polynomials again, right? Well, so the only thing we cover for this section is the remainder theorem and Taylor's inequality. And well, this is to determine how good approximations can be, because, well, again, keep in mind what we have been doing for the last few days is approximate functions with polynomials, and then use those polynomials to approximate the value, say, the square root of 17, sine of 1 degree, or e to the second power, but instead of using the exponential, the trigonometric, the radical, so we use it using polynomials. And that's because these polynomials happen to converge to more values rather than some potential pitfalls with the actual function that they represent. However, well, so the question is, how many terms do we need to add in our approximation to get a desired approximation? For example, okay, let me give you an example with a numerical example, like 1/3. What is 1/3 equal to? Or, well, you think of 1/3, what is that equal to? 0.33, right? So this is approximately 0.33. And, well, this is only an approximation. However, if we want an actual, the actual value, this will be then, okay, 1/3 equals to 0.33. If we change the approximation symbol to an actual equal symbol, this will be 0.33 plus some remainder. It remind. Wait, I think it's right. It's a remainder. In the same way, okay, we can also approximate 1/3 to 0.33. A lot of threes, If I add more digits here, I'm coming up with a better approximation, but that's still an approximation because this number, it's called periodic. That is, it repeats on and on infinitely many decimals. So we are still working with an approximation plus some remainder. All right. So together, the approximation plus the remainder, that adds up to the actual value. All right, so this is the example with a numerical example now. So with functions, actually a function f of x can be essentially broken up into two parts. The Taylor polynomial in general, which could be it could be a Maclaurin polynomial if we expand the polynomial around 0, of course. But again, whenever we do, the 3rd degree polynomial, the 5th degree polynomial, even though in some cases the approximation is good, that's only what it is. It's only an approximation. It's not the actual value. So we are leaving out infinitely many terms. All right, we're just using, say, 5 terms, 7 terms, 15 terms. It's just an approximation, and that's the remainder here. Now, if we take the limit of the remainder, the number of terms, if we make that, if we use rather infinitely many terms in our approximation, well, that means that the remainder is 0 because, well, we're using infinitely many terms. We're not leaving any room for approximations. In fact, we are coming up with the actual value. All right. I said, let me give you another example now with functions. For example, if we have the function e to the x, e to the x, well, we can expand a few terms of its polynomial form. Actually, I'm going to use the Maclaurin polynomial, you know, just so we don't get into too many details with the expansion. So the Maclaurin, that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And well, if we use, in this case, p sub 3, well, then we are going to have a remainder and this will be denoted the remainder due to using the third degree polynomial. Okay, so that's the remainder related to obtaining the third degree polynomial. That is, well, of course, infinitely many terms that we're leaving out in the approximation. That is the degree 4 and on. Likewise, well, if we want to come up with a better approximation here, well, so let me make this a little smaller. Nope. If we want e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial. Well, in this case, we're using P6. And that is the polynomial of 6th degree, Maclaurin polynomial of 6th degree, which, well, it's going to give us a better approximation. However, this is not the actual value. That's just an approximation up to the 6th degree polynomial. So in this case, we will start getting another remainder. But this remainder will be the remainder r of using the 6th degree polynomial. Alright, in this case, well, it's going to be a polynomial of 7th degree and on, basically degree infinity, if you will. Alright, so let's see. Now the question is, the idea is that depending on how many terms we use for the approximation, the more terms we add to the polynomial, the better the approximation. And that's something we looked at last week when we discussed Taylor polynomials and Maclaurin polynomials, when we did the exponential, you know, so we got the linear approximation. Then we also got the quadratic approximation. And by the time we got to the quartic approximation, that quartic approximation was overlapping the e to the x function to more points as opposed to just a linear approximation, which was it was a tangent line, just overlapping one point, but still an okay approximation. It's still an okay approximation around the center point at just a small number of values. Now, and here, this is the picture, so to speak. So we have some function f of x, you know, and well, let me call it like this. So that's the function f of x, and this is the approximation. This is the approximation around a, for example. So we're going to look at an interval a minus c to a plus c, so to speak. And well, so the further we go from the center of the approximation, notice the phenomena that occurs here. So the further we go, the actual value starts differing from the approximated value, and the same phenomena occurs on the right hand side. So we're going to use Taylor's inequality to find, well, in terms of a percent, what's the percent, how off are the actual value from, or from the actual value from the approximated value using this inequality. And well, for this inequality, which is in the definition box here, so, and well, so in this case, this okay, we're just going to look at this using an example. This inequality is kind of weird because, well, so if the next derivative is less than some upper bound m, provided x minus a is less than or equal to d, well, then the remainder Rn of the Taylor series satisfies the inequality. That's Taylor's inequality. R sub n less than big M, which is the upper bound in the inequality, over n plus 1 factorial x minus a inside of the absolute value bars to the n plus 1. That's actually the next term, you know. So for example, if we use the second degree polynomial to approximate, well, then the error, or yes, the margin of error will be given by the following term in the series expansion. However, before looking at the example, it's important to understand how inequalities work and how do we interpret these inequalities. You know, for example, whenever we see this inequality right here, what is that inequality telling us? If we were to describe it as a set. From negative infinity, so this is the set of all points from negative infinity to 3, including the 3, right, in this case. So, or all the set of all values that are less than or equal to 3. In the same way, this is the set of all, well, not all points, let's call it all values actually, because we're not looking at ordered pairs. The set of all values from negative infinity to 3, and in this case, the set of all values from 3 to infinity. All right, but I mean, what are the implications of this inequality? Well, maybe this is not the way. What I'm going to do, what am I about to write down here, you may have not interpreted this inequality the following way. And it's important to have an understanding of inequalities this way, because that's going to make a huge difference when setting up the Taylor's inequality problem. All right. Okay, so the fact that we have all these values from negative infinity to 3, well, how about we graph them? So that's a 0, that's 1, 2, 3. That's basically this inequality. All right? So another way to interpret this inequality is to say that this set has a maximum value, all right? Equals to 3. So this set can contain any number from negative infinity up to 3, but I mean the largest value that this set attains is the value of x equals to 3. On the other hand, for the other inequality, 0, that's 1, 2, 3. So that's just gonna go this way. All right, and in this case, this set, which starts at 3, 4, 5, 6, 7, infinity, this means this set has a minimum value. Of 3. All right, that's another way to interpret inequalities. And well, you may not have seen inequalities this way, but well, now you have it. And again, We need this for our exercise over here. All right, so let's go about the exercise here that we have about it. So what are we going to have? Approximate the function f of x equals the square root of x in a Taylor polynomial of degree 2 at a equals to 8. And by the way, there's a little typo here. This one was supposed to be f of x equals the cube root of x, not the square root. Okay, so just for those of you who have the PDF file or the printed file, just change it for a cube root. All right. So number one, we're going to obtain a Taylor polynomial of degree 2, and then we're going to see what happens with the next term. So number one, f of x equals the cube root of x, and I'm going to rewrite as x to the 1/3 because we're going to take a few derivatives in here, all right? And then evaluate f at 8, that's the cube root of 8, which equals to 2. Let's take the first derivative. The first derivative, which will be one using the general power rule, that's 1/3 x to the negative 2/3, and we need it in at least positive exponent form, so we can evaluate f prime of 8. That's 1/3 times 8 over 2 to the 2/3 power. And well, simplifying this expression using a calculator, well, actually no decimals for this, that should give us a 1/12. Then taking the second derivative, that's going to multiply negative 2/3 times 1/3. That's going to be negative 2/9. X to the negative 2/3 minus 1, that's basically negative 2/3 minus 3/3, that's a negative 5/3. And well, we also need it in positive exponent form, so we can easily evaluate it at 8. So that's a 2/9 times 8 to the 5/3. And well, simplifying this expression, take the cube root of 8, which is 2, raise it to the 5th power, that's 32, times 9, big number. After simplifying this, that should give us negative 1/144. And well, although they're asking us only for the second degree polynomial, because for the error estimation, or to study what about the accuracy in the interval 7 to 9, we need one more derivative, one more term, one more coefficient, or maybe we don't need a coefficient, or maybe we will. Well, anyway, find the third derivative, and well, negative times a negative equals positive. 2 times 5, that's a 10/27. X to the negative 5/3 minus 3/3, which is 1, that's a negative 8/3. All right? No, we're not going to evaluate this derivative. All right, so we have all the information we need to get the second degree Taylor polynomial, second degree polynomial. These are going to be the coefficients of the Taylor polynomial, the ones that I'm highlighting in this case. All right. Well, so let's set up t sub 2 of x equals f of 8 plus f prime of 8 x minus 8 over basically 1 factorial, which is 1. Over here I was supposed to write x minus 8 to the 0 power over 0 factorial, but all that simplifies to 1. And f double prime at 8 that times x minus 8 squared over 2 factorial. All right, so let's write down the corresponding coefficients, all these numbers that I'm highlighting here are the coefficients that we found in the previous part. And well, t sub 2 equals to 2 plus the derivative evaluated at 8, that's 1/12 x minus 8, plus the second derivative evaluated at 8, which is negative 1 over 144 x minus 8 squared, the whole thing divided by 2 factorial, which is 2. And well, we need to simplify this, and that's going to give us t sub 2 of x equals to 2 plus 1/12 x minus 8 plus, or rather negative, minus 1 over 288 x minus 8 quantity squared. So that's our second degree polynomial, and we use it to approximate the cube root of x at a equals to, or around a equals to 8. So that's what we're doing. All right. So that polynomial, yes. Oh, 2 factorial is 2, and 2 times 1 times, well, we stop at 1, right? And then, well, dividing by 2 is the same as multiplying by a half. 1/2 times 1 over 144 gives us the 1 over 288. Well, so so now we want to find that error. And again, the picture here is, okay, let me just draw a very generic graph. So we're looking, this is the graph of x equals to cube root of x. Well, of course it has a negative tail, but we're just looking at the positive part of the tail. So that's going to be 8, and we're looking actually between 7 and 9. All right, we want to know what happens as we get away from the center, which is 8. But in this case, we are bounding this this interval to just 7 and 9. And for example, here we're going to have our approximation at this point. So suppose this is our polynomial approximation t. Let me label it as t2, and let me label the other one as our f of x, in this case the f of x, which is the cube root of x. All right, so the thing here is at the center, well, of course the approximated value is exactly the same as the actual value. But if I go a little bit towards the left, do you see the difference here between the actual value and the approximated value? And that starts getting bigger and bigger. That difference gets bigger and bigger all the time. However, the question is, what's the worst case scenario, or the least accuracy at the bounds? The same thing happens over here. So, well, maybe not, maybe up to here, right? So we will reach, what I'm trying to say is that we will reach a maximum difference, and that maximum difference will be given by Taylor's inequality, which, by the way, let me go back to the Taylor's inequality definition. Did you see the form of the inequality? Forget about the madness. It's an inequality of the form x less than or equals some number a. That means this set x less than or equal to a, it's going to attain a maximum, which is going to be a. And that means all these quantities right here that we will compute have to be the largest of them, so that we can find out what the largest value is. Well, let's actually go about the exercise using the inequality. Well, so number 1, Taylor's inequality, the absolute value of Rn, that is going to be less than or equal big M over big M over n plus 1 factorial absolute value of x minus a to the n plus 1. Alright, well, so there's a couple of things that we need to make sure. Number one, well, n factorial, n plus 1 factorial, rather, that's just going to be the index, you know, like number 2, number 3, and in this case we're using n equals to 2. So, for n equals to 2, that's the remainder of just using the second degree polynomial. That's going to be all absolute value actually. Big M over 2 plus 1 factorial x minus a 2 plus 1 factorial r sub 2 m over 3 factorial x minus a over, well, actually in this case is 8, right? To the third power. Alright, so again, there's two quantities that we need to compute. Number one, the one quantity that we need to compute here is this big M, and another quantity we need to compute is this absolute value of x minus 8 to the third power. Now, so since we want the inequality of the form absolute value of r sub 2 less than or equal, well, even if it doesn't have an absolute value, well, in this case it has an absolute value because it's an interval. We want to make sure that we have that sense of interval by having this absolute value to break it up into two quantities. Well, we want to make sure that this m is the largest possible and this absolute value of x minus 8 to the third power is also the largest possible, because in this case if we obtain the minimum, well, that's not going to give us the maximum error of expanding about 8 within the interval 7 to 8. So we want to know the maximum value in this case. So I'm going to compute these two quantities separately. On the one hand, I'm going to compute the quantity x minus a to the third power minus 8 to the third power, and well, notice in this case we can evaluate this inequality, or rather this expression, at two different values. Number one, though, that's going to be the endpoints of the interval that we want to study about this Taylor approximation. So for x equal to 7 and x equals to 9, well, we're going to obtain two results: absolute value of 7 minus 8 to the third power, that's the absolute value of negative 1 to the third, which is just 1. On the other hand, 9 minus 8 to the third power equals 1 to the third power, or absolute value of 1, and that's just 1. So in this case, that doesn't really matter. We can take just 1. Actually, we can already say that this value right here equals to 1. Well, notice I'm doing both sides of the inequality just to make sure that we get the same value. But it's not always the case that it's going to be a 1, depending on how wide that interval that we're looking at is. In this case, it's only 1 unit away from the center. Now we need to maximize this value of m. I mean, I guess the uppercase letter gives us a hint that that has to be a big M, big value, you know, the largest, the maximum. But in this case, how do we get that maximum value? Well, in this case, that's m. Well, how do we get m? So we have that the absolute value of the n plus 1 derivative, that is the one for the next term at x, has to be less than or equal to big M, where big M will be, it's actually the third derivative. Well, let me set it up as a third derivative. That's 2 plus 1. The third derivative of x All right, so, and that's why we took the third derivative, even though we didn't evaluate it before, so we're going to use that third derivative. And okay, so let's find the value of m. Well, it's actually just less than, I think. So, m, it's going to be the third derivative, which in this case is 10 over 27. And I'm getting this from that third derivative I found over here. That's 10 over 27 x to the 8th thirds. All right. So 10 over 27 x to the 8th thirds. Now from here we have two possibilities. Evaluated at x equals to 7 and evaluated at x equals to 9. In this case, we need to decide which of the two evaluations it's going to give us the largest value for m. Any ideas on which one is it? Okay, it's 7 because 7 is a number smaller than 9. Do we agree with this? And while having a smaller number in the denominator is going to give us a larger value as opposed to plugging in the 9. That's going to give us a larger value in the denominator, and while it's a smaller number, and that's not going to give us the maximum value. So, and we want to obtain the maximum in this case. So let me cross this out. And again, as a note, need to check both and determine which one is the maximum actually. All right, so that's gonna be what is this? 10 over 27 times 7 to the 8th over 3. Let's leave it like this. I know this is a very funky number, so let's leave it like this. So now that we found m, that's going to be this number. It's going to make it the maximum. All right, that way we can get the maximum error. And well, so we may now go back to Taylor's remainder inequality. That is, the absolute value r sub 2 is less than or equal. So number one, this funky number 10 over 27 times 7 to the 8th thirds times, remember this invisible one that I wrote here? I'm going to still write that invisible one and divide that over 3 factorial, which in this case is 6. All right, so well, let's just rearrange this funky number, this madness here. And that's 10 over 27 times 7 to the 8th thirds times 6. And after simplifying this, by the way, this is the same example as in the textbook. One thing I disagreed with the textbook here is that they were rounding within every single calculation. Recall that, I mean, this is a rule of thumb in science and also in mathematics. I don't know why the author of the textbook actually rounded before we were supposed to. So after simplifying all this, the remainder of using the second polynomial, the second degree approximation, is 0.0034. Well, all this crunching of numbers, symbols, inequalities, what does that value represent? Well, so remember when we looked at this inequality here? So I mean, x less than 3. So I mean, that set of values contains all the numbers between negative infinity and 3. That means in this case the maximum value contained in the set is the number 3. In this case, looking at this inequality in the form of a set, that means that the error of using the second degree polynomial is at most, the maximum error is 0.0034, which is the same as saying 0.334%. That means in the worst case scenario, what do I mean by the worst case scenario? Let me go back to the graph right here. So, again, we look at the center. I mean, exactly at the center, both the approximated value and the actual value are the same. If we start going some value towards the left or towards the right, well, that's where the two values start differing, right? Well, at the endpoint 7 and 9, this means that largest difference between the approximated value and the actual value is at most 0.34%. All right? That's what that value from the inequality that we obtained represents. Well, of course, I mean, here we can ask ourselves, what would happen if we went to the interval, say, 6 to 10? Would this 0.34%, would it be a smaller number or a larger value? What would that be instead? Anyone? Yes. Exactly, larger, because we're getting further away. Now, if we want to keep the interval 6 to 10, what would we need to do in this case to reduce that error? Add more terms. Maybe not one more term, maybe 2 terms, 3 terms, 4 terms, you know, etc. Well, and I mean, this is something that most of you as engineers, you're going to work in a lab in quality control or in designing pieces for or parts for cars, airplanes, etc. So you want to make this with a really, really good accuracy, you know, and well, so really the math behind, or the art behind, if you will, is to make this better, to make these improvements by, you know, in this case, well, you don't want this the specifications in the manufacturing, you don't want this error. This is not an acceptable error. Most likely at industrial level, you want accuracies to be a lot closer to the actual value, and of course you will have computers to compute these calculations for you without you having to take, I don't know, 100 derivatives. You know, you don't want to do that by hand, right? So but well, this is really just the idea behind how what's the worst case scenario on certain endpoints of an interval when we're using given an approximation to a quadratic in this case, and versus the actual value. All right.